Hey, welcome back to another episode, and today we're continuing on in our bit of a material science journey, and we're trying to make some perovskites. More specifically, we're trying to make perovskite nanocrystals, which should be highly fluorescent. So once again, all of this work is just to make something that glows really cool. That's the aim. If it glows cool, we've done it. But before we get to the synthesis plan, there's an obvious question, which is, what the hell is a perovskite? Perovskite is originally a geology term, so it's a name of a mineral structure, and that's not really what we care about today. We're not doing geology. We don't really care about perovskites, natural perovskites. We care about synthetic perovskites. It's kind of not very common for material science and chemistry to take a word from geology and apply it to a range of structures, but it works here because the structure is important. The structure of the materials are important, and it's also kind of good for propaganda reasons, I would say, because what people are most excited for them is in solar cells. And it's a lot easier to say, wow, look at these new perovskite solar cells. It sounds amazing, rather than saying, we've just invented a new lead halide solar cell. There are lead-free perovskites, and people are trying to work on lead-free versions. They're all worse than the lead version. I mean, I love lead. I've said this a couple of times. Lead is a fantastic element. It's widely abundant, it's cheap, it's easy to recycle, it's got a huge number of upsides, and pretty much one downside. Perovskite solar cells are the most efficient solar cells, really. They keep breaking their own record. Depending on when this video has got published, they've probably broken the 30% efficiency record, which is better than, any sort of silicon solar cell. They've got a lot of problems with degradation in the environment when they get exposed to too much UV light or like moisture and stuff. They tend to break down, which means they don't have that high efficiency for very long, and also they start leaching lead into the environment, which is a really bad thing if you're thinking about rooftop solar, because that's where a lot of the world gets their drinking water from, the roof. So you can't put the lead leaching panels there. But those problems may be solved. People are optimistic that the degradation problems will be solved, and then we'll have more highly efficient solar panels. Perovskite nanocrystals is what we're making today. Rather than taking light and turning into electricity, we're just focused on making them fluorescent. They are highly fluorescent, and you can change their color by changing the anion. So the one we're making today is the classic perovskite, the cesium lead bromide, but we should be able to tune that if we do successfully make it by swapping in and out chloride and iodide, and it just really comes from the structure itself. It's a bit weird to think about because often people think about fluorescence as just like an ion in there that's fluorescing, like a rare earth ion, but the cesium, the lead, and the bromine aren't getting directly excited. It's a semiconductor material that's kind of generating charge pairs, which then recombine and cause fluorescence. So it's the structure itself that's important, and that's what's driving this sort of light emission. That's an extremely quick overview of the physics behind them. So to make this classic cesium lead bromide, we're following a 2018 paper, which is, fairly recent, and it uses mechanosynthesis. That's a really fancy way of just saying we're going to crush it. We're just going to make bulk perovskite, and we're going to put it in the ball mill, and it's going to be ground down into little nanocrystals, which should be really fluorescent. I think it's really cool science that you go from sort of a bulk material that has no fluorescence, but then once it's crushed down, it is brightly fluorescent. So we should hopefully be able to see that. But there is a lot of work to do because, as usual, we're trying to do this using chemicals we can get from the hardware store or just easily available online. We've got to start with lead bromide and cesium bromide, but we can't just get those chemicals, so we have to make those chemicals as well. So what are our actual starting materials? We've got to start a couple of steps back. We can start from lead metal. Lead metal is pretty easy to find, I'm fairly sure. Last time I checked, which is quite a few years ago, there was still pretty easy to get as like diving weights or fishing weights or something. So unless they've all been phased out and are just using bismuth now, I'm pretty sure we should be able to get some lead. Most of the lead metal I've used previously, I found in a field, I'm fairly sure, just a chunk of lead from a roof or something like that. So all the lead chemistry I've done previously has just been off this chunk of lead from a field. So maybe we can just go through a field and see if we can find any more lead. But we can dissolve it up with nitric acid, form a soluble lead, and then precipitate out lead bromide with sodium bromide, which we just get from eBay as like a bromine pool chemical, bromine spa chemical. Cesium bromide is a little harder. Cesium's not super easy to find, but I do just have some cesium carbonate in stock here in my lab. It would be great if every synthesis I could just work up from gasoline and a ham sandwich. But yeah, we do actually need cesium, the element itself, and we're not going to get that from the hardware store. But yes, cesium carbonate to cesium bromide. I've been trying to think of an easier way to do this, but really the best way I can think of is using hydrobromic acid, which is reasonably straightforward, but it does require us to make our own hydrobromic acid because I don't have any of that, which we can do from sulfuric acid drain cleaner and the sodium bromide, which we need to get for the lead bromide anyway. Altogether, if we make the hydrobromic acid and the cesium bromide and the lead bromide, all we have to do then is combine them all and grow crystals of the cesium lead bromide, which in the paper they do from DMSO. So they combine them all and heat it in DMSO and it grows these really nice crystals. The paper does mention that you don't really need to do this step. If you've got the cesium bromide and the lead bromide and chuck them into the ball mill and mill it, it does form the perovskite nanocrystals, but the fluorescence isn't as good and the crystal quality just isn't as good. So I think it is worth the extra step. Make the bulk perovskite structure first and then crush it down rather than trying to do everything in the ball mill. I'm hoping today in this video to make it up to the cesium lead bromide, the bulk structure. I don't know how far we're going to get. I haven't done it yet. I have no idea. It's just one slight issue with the paper is that they use oleamine, which is a chemical. I think it's used as sort of a surfactant. It has a number of roles, but they add it into the ball mill. And this is what all the papers in this area tend to do. They all tend to use oleamine. And it's not really a chemical I can find. It's not really widely available. It's sort of a cheap industrial chemical, but it's not really something that's on eBay or at my local hardware store. So that's an unsolved issue. So we're starting the synthesis even though I haven't solved all the issues yet. So if you have any suggestions on either where I can get oleamine, maybe I could make oleamine, but maybe you can suggest a paper where they do it without oleamine. It might work without oleamine. I keep saying oleamine a million times. Anyway, that's where we are. This is the synthesis pathway. We've got a lot to do, a lot of chemistry. Let's get to it. I'm excited. Let's get to it. All right, here we go. We are going to be following Nerd Rage's method. I mean, he didn't invent the method, but I'm basically following his video exactly in terms of getting hydrobromic acid from sodium bromide. At a slightly smaller scale, we really do not need very much hydrobromic acid, maybe a couple of grams. A part of me thinks, well, if we're going to do it, we might as well make like a liter of hydrobromic acid. It's not something I think will be super useful in the future, but yeah, I don't know. So we've got 100 grams of sodium bromide. That'll be way more than enough, and we can keep some on hand for, I don't know, if we want to do this again in future or something like that. Nerd Rage uses drain cleaner sulfuric acid, concentrated sulfuric acid, which is what I would do as well. It does feel a bit weird sometimes to use the concentrated sulfuric acid, which is actually still quite expensive in this drain cleaner form, and then dilute it, seeing as I have like 50% sulfuric acid. But this reaction is extremely tolerant to bad acid because we're just going to be distilling over the hydrobromic acid with quite a bit of water in the first step anyway, so it doesn't get that hot, so you can have all these contaminants in it and it's not really going to affect the hydrobromic acid too much, which leads me to this pile of very old sulfuric acid. Well, some of it's not too old, but pretty poor condition stuff. Like I said, this stuff is expensive and haven't always had a lot of cash to burn on experiments, and it was actually quite hard to get. Not a lot of stores stock the sulfuric acid, so I used to hoard it quite a bit. This I made from some battery acid long time ago. Anyway, I saw these in the back of the cupboard and thought I really should have got rid of these years ago, but the next best time rather than years ago is now, because I shouldn't see them there and just leave them in there. Where's this from? Trinitromethane, November 2016. Hydrogen sulfate. I mean, this is what the acid looks like straight out of the bottle. It has this kind of brown color. Trinitromethane. Well, I should revisit that synthesis. That was 2016. Christ, 8 years ago, yeah. Never really got that working. Interesting if I got that working. I should try that again. Anyway, I'm getting distracted. Should I use this acid? Probably not. Now I look at it. Maybe I'll use this one. We just want an excess of acid, so we don't really care about like concentration or how much we use or anything like that. I've just got a little bit left in this bottle. Maybe I'll just use this little bit of the bottle, and if I've used this up, then I'll use some of this and I'll just get rid of these ones. It's kind of fun holding onto samples for historical value. Kind of shows how far you've grown, because this is probably 2015 or earlier. Took the effort to distill down bloody 30% acid, and now I just dropped $60 on a litre of concentrated acid without even thinking about it. But You can't be too sentimental with bloody concentrated acid samples in a wine bottle. You know what I mean? I'm telling myself this. I got to get rid of them. Anyway, so let's get it all into this thing and set it up for distillation. I'm so sorry it's so windy. If it gets any windier, I think I'm going to have to abandon this experiment. It's pretty damn windy, but you know, other than that, it's a beautiful day. So I'm trying to ignore the wind, even though it's probably making the recording very, very bad. But it's such a nice day otherwise. Sometimes I forget to turn the radio off. Sometimes the compressor or the generator turns on in the background and it's very windy, you know? But it ain't about the production quality. I'm just genuinely wanting to do this. Seems we've reached pretty much the end. I was expecting this mix to solidify a lot more, probably because we used quite an excess of acid, even more than I guess Nerd Rage did. And we really don't care about yield too much. This is heaps of acid. Once again, I need a couple of grams of hydrobromic acid. What we don't want is we don't want to pump over heaps of sulfuric acid. Well, we really don't want to have any sulfuric acid in here. You might just have to check to see if there's any sulfate ions in our distillate here, and if there is, we'll just have to redistill it and actually put some care in, you know, actually monitor the temperature. Still quite a bit of liquid left in this flask. Sorry, I've got to try not to care so much about yield when it's not important. We will be using this directly to make the cesium bromide, so if this is pure, we can just add the cesium carbonate in and evaporate it down and get the nice crystals, but if it's got some sulfate ions in, we just add in the cesium carbonate and evaporate it down, then we'll just have a really impure crystals at the end there. And so if we purify it here, then the cesium bromide we get should just be pure straight out of the reaction mix. Okay, to test if we have any sulfate ions, I have here a big container of calcium chloride, a little bit of water here. Let's put in just a couple of crystals, well, sort of lumps. Don't want to do too many lumps. There's a lot of it in here. Oh, gentle, gentle. There we go, get that dissolved up in the water, and we're just going to add in, a couple of drops, maybe a ml of our hydrobromic acid. Calcium sulfate is very insoluble in water, so if there's no sulfate ions, we won't see anything. But if there is sulfate ions, it'll precipitate out calcium sulfate, and we'll see that as a white precipitate. It'll go cloudy. So if this test comes up clear, I'm pretty happy to continue with it as is. Although it's got a bit of scunge in it somehow, not the VB bottle. Is it scunge? There's a bit of floaties, you know? How they make their way in there, I'm not entirely sure. But we'll just filter it to sort of defloaty it. Maybe some bit of glass that wasn't too clean. Yeah, there we go. Now you can see it. Ugh. Where'd that appear from? Gross. Anyway, we'll filter them out. Fuck knows where they've appeared from. Looks pretty clear. Looks all clear, so I think we're all clear. I'll just add in some sulfuric acid just to show what the precipitate will look like if it was actually had sulfate ions in it. Put it in. You can see that precipitate down the bottom. Obviously, one last check. Let's just check it's actually acidic, so we haven't just distilled over water. Yeah, look, extremely acidic, as we'd expect from hydrobromic acid. So great. Apart from the scunge, as per usual, it looks pretty good. So we have a hydrobromic acid. We still don't know the concentration. And once again, for this reaction, we don't care. But if we are smart about it, I suppose we can work out what the concentration of the acid roughly is while we do our experiment, because this is our cesium carbonate. It was nicely labelled at some point. The labels fell off, so really should relabel these so they're not just random vials of unlabelled white powder. But if we know how much acid we have and then we use a small percentage of that to neutralise, say, 5 grams of cesium carbonate, then we can work out, you know, the molar percentage of hydrobromic acid, because, you know, we know how much mass of acid we've used and how much we've neutralized it. We're basically titrating it in this experiment. Anyway, getting bogged down in these details. It really doesn't matter too much. 5 grams, how much should I use? I mean, we really do not need very much. We're making nanocrystals at the end. Like, it's not going to need very much material, but I'm really bad at doing small scale chemistry. So I think 5 grams is good. This is all the trash from the hydrobromic acid distillations. There's still probably some sulfuric acid and some bromide in there still, but mostly it's like sodium sulfate and sodium bisulfate that's crystallized out as a reaction mix called. Should be easy enough to clean because they're pretty water soluble, but now that the cesium side of things is reasonably sorted, it's onto the lead. Lead is pretty cheap. But I love a lead source, a source of any chemical that I can get from the hardware store. At the local hardware store, they sell sheets of lead. This is nearly 3 kilos of lead. Actually, it's a bit over 3 kilos. It was like 40 Australian dollars, which, you know, is pretty expensive for lead. But in terms of buying an element from the hardware store, it's pretty good. I thought it was pure lead, but now that I'm home and I've learnt to read, this says copperized lead flashing. Copperized means that, well, as you'd expect, it's got copper in it. Some places say it's like a matrix of copper, which makes me think it's kind of like a scaffolding for the lead metal to be on, in which case we should just be able to melt the lead off that copper. But they might also be using matrix in a sense that it's kind of just an alloy, and you're using matrix. It's kind of more of a buzzword. In which case, if it is an alloy, we won't be able to melt the lead away from the copper, but it should still not chemically interfere. How we're doing it is we're going to dissolve it all up in nitric acid, and everything should basically dissolve in nitric acid, and then we'll precipitate out in the lead bromide with sodium bromide. The copper 2 bromide is quite soluble, so we're not going to have any copper precipitate out with our lead. I think so anyway. I should look that up. Anyway, I thought this was funny to buy sheet lead. I like this. You know, the width is 450. The length is also 450 millimeters, obviously. But here they've made a typo and input 1M. So someone has gone through by hand and corrected them all. So I don't know what poor employee got that job to change them all to 450 millimeters in case someone thinks there's 450 meters worth of lead in here. It's hand done. Anyway, classic. Thank you. Well, something that's actually made in Australia. We did it. All right, let's crack this open. Smells a little more. Right, I'm unsure if we really did anything there. I think the lead looks a little nicer. It's definitely more artistic. compared to this lead sheet. Yeah, I don't really know if we've left much copper behind or sort of refined the lead out of the copper at all. I don't even know how much copper's really in there anyway. Doesn't really matter. It was fun. And it's not like I'm short on lead. This is actually over 20 grams, and really I just don't need to dissolve that much lead up, so I'm really only going to use 10 grams. But yeah, 10 grams out of all this is not very much. I should not have bought this much lead, but you know. How much is that? 9.7. Round number? Yeah, 10.2. 10.2 is fine. So our next step is to dissolve this metal up in nitric acid without giving ourselves lead poisoning. Soluble lead is a lot worse than lead metal. So also, I've got to clean this area up. I've cut the lead and I saw little bits of lead go everywhere, so I really got to wipe all this down. I really thought the Stanley knife would be good at this job, but it was abysmal. But tin snips were ideal, really. Maybe one day someone will use this for actual lead flashing, whatever it is. Protect joints. All right, we have here 10.2 grams of lead metal. It's just in a little bit of distilled water. I'm going to be adding in, oh man, the cows are going at it. Anyway, we're going to add in some nitric acid. We don't want it to get too violent. Obviously, we don't really want to spray lead into the air. So nice gentle bubble. I shouldn't need to heat it too much. Once it's all dissolved, we're going to add in sodium bromide. I feel like there's going to be no issues, so I'm just going to try and speed through this so we can get through the rest of this in the montage, you know? Once all the lead is dissolved, we need to add sodium bromide in to precipitate out the lead bromide, which will filter off and collect. We've got 10.2 grams of lead, so we need at least 10.2 grams of sodium bromide, which sounds made up, but sodium bromide is about half the molecular weight of lead, and we need 2 times as much sodium bromide because we're making lead 2 bromide, so that's why that maths weirdly works out to be the same number. Yeah, we'll get it all dissolved and then add in our sodium bromide solution once it's all dissolved. Here is our brilliant white lead bromide, which basically completes this step. It's mostly dry. I washed it with ethanol and acetone, completely insoluble in those solvents. So it should dry reasonably well. That's all good. Just a couple of notes. Obviously, this is the solution that was left over from it. Lead bromide has a reasonable solubility in water. I think it's about 0.5 gram of lead bromide per 100 mils. So that still contains quite a bit of lead. So we're not just going to put that down the drain. Not that we were going to do that anyway, but this old bottle of lead waste, which I'm adding in sulfide ions, or have done that previously. Lead sulfide has a very low solubility, so soluble lead is quite toxic, and even when we dump it in here, it will still be lead waste, I guess, and we have to, dispose of it at some point in the future. But the actual toxicity, I mean, kind of, I guess, the real risk from it is a lot lower because, if it's insoluble, your body can't process it. Wikipedia lists a solubility for it. It's kind of funny. Instead of just saying it's insoluble, it lists a solubility, which I think it lists a number that's 10 to the minus 12, which is honestly impressive. They can measure a solubility as low as that rather than just saying insoluble. But anyway, I'm getting caught up. Yeah, so obviously lead waste. This was the solvent washings in terms of the ethanol and the acetone. I was thinking they might be clean, but yeah, it looks like some more is precipitated out down here. Whether that was just residual water solution causing some to precipitate out, but it doesn't really matter. These are all going in the lead waste. What is our next step? We've got to remind ourselves. It is, now that we have lead bromide and we have cesium bromide, we need to dissolve them both in DMSO and then heat the DMSO up slowly to form crystals of our cesium lead bromide. That's great. So we just need some DMSO. I was going to use this. This is obviously from the hardware store. 10 to 30% dimethyl sulfoxide, so that's DMSO. It also has 10 to 30% ethyl 3-ethoxy propanoate, which is, I don't know, something random. So I was going to use this as my DMSO source. Maybe I thought maybe we could just use this as is, but then I thought about it a bit more. I mean, this is goopy. It may only be 10% DMSO, so I don't think it's going to work particularly well. So I went out and bought some DMSO, which still feels kind of in the spirit of hardware store-ish, because you can get DMSO just from eBay. Strangely commonly available. Well, there's a reason it's commonly available, and I don't like that reason. The reason it's widely available and easily bought is because people use it as an alternative medicine, so that drives a market for it. So it's kind of annoying to buy. Well, it makes me feel bad that I'm kind of supporting people who are selling alternative quack cures for people who are quite often quite desperate and looking for a cure for things. And buddy, you look this up online and this can cure everything from cancer to arthritis to everything, and it's very sad that people take advantage of sick people in that way. And what's also strange is that in Australia, which is where I got this from, OzChemSource, this is a Schedule 4 drug. They added DMSO to the Schedule 4 list. Now, Schedule 4 is one of the lower ones in terms of drugs, so it's on the same sort of tier as like tramadol and SSRIs, so you're really only meant to get this, I guess, as a drug if it's prescribed to you. Should I be able to buy pharmaceutical grade flammable solvent from the internet if it's meant to be a scheduled drug? I don't know. Should it be a scheduled drug? Should it actually be policed as a scheduled drug if you're going to add it to the scheduled drug list? Obviously, the defense of the sellers, OzChemSource, is just saying, oh, well, obviously we're not selling pharmaceutical grade DMSO for people to use it as a medicine. Well, then why is it labeled as pharmaceutical grade then? You're obviously taking advantage of sick people. Even though it should be illegal, well, it is illegal for you to sell this for use in pharmaceuticals. Anyway, rant over. This is DMSO, great. So it smells bad, is a fantastic solvent, has a high boiling point, has polar aprotic, which is kind of a weird class of solvents, but makes it very, very good. It's also got a melting point at, 19 degrees or something like that. So good old Australian temperature. Oh, it's a bit slushy in there. It's a European problem for the DMSO to always be frozen. In Australia, your DMSO is very rarely frozen. Oh, the thing about DMSO being such a good solvent is kind of why it can pass through your skin very easily. And also these gloves, these nitrile gloves, which are not very resistant to DMSO, but neither is your skin. And that's kind of why it's a weird alternative medicine, because it does actually pass through your skin very easily. And so if things are dissolved in DMSO, it can carry those dissolved things through your skin. It does become a little concerning to me if you're making let's say, a concentrated lead solution in DMSO. Because if I spill, say, this is a concentrated aqueous lead solution on my hand, I mean, it's bad, but I'm not going to immediately, I guess, be exposed to that lead in the sense that that lead isn't going to go into my bloodstream straight away. But concentrated DMSO solution with lead in it, and I spill that on my hand, even with the gloves on, it's going to transfer through my skin and carry that lead directly into my bloodstream. Obviously, the paper doesn't mention anything about this. It's just kind of assumed. You're like, haha, lead in DMSO. Sounds like a good time. We are going to be extra cautious here. Let's say that. Apart from that, apart from all of these issues, I think we're good to go to start dissolving up both our cesium and our lead in the DMSO. We're going to try and get as much as we can dissolved. It does say then it's filtered at room temperature, so I assume some of it doesn't dissolve, or at least maybe there's just some sponge left, let's say. But then we have our nice clear filtered solution, and we'll start heating that up slowly, maybe in a water bath or something up to, well, I mean, we want to get it to 110, so maybe an oil bath. We'll heat it up slowly, see if our nice crystals form. And once again, we're looking for orange crystals. We've got a white powder here, white powder there. This is just a clear solvent, so it should be pretty noticeable if we start growing big orange crystals. We're gonna give it a shot. All right, stay safe everyone, let's do it. Hell yeah. Hell yeah, now that's chemistry. God, imagine if every reaction worked this well. Just weighing the stuff out made it work. Oh yeah. And everything has dissolved, which is surprising. Well, pretty much. We'll give it a quick filter as per the synthesis suggestion. We've got another little vial here, a little bit of filter paper and a funnel. Just pipette it across without spilling any drops. It is surprising that much solid really dissolves in it, but I guess that's the magic of DMSO. Not expecting to see such wonderful colours so early, but yeah, fantastic. Now everything's basically dissolved. The solution itself is not that fluorescent. Once again, you know, this is a solid state fluorescence that we're looking for. Well, and actually, we're not really expecting to see that much fluorescence from the bulk solid anyway. The whole point of the synthesis is to make the bulk solid and then grind it all up. And once they're nanocrystals, they'll be really bright. So the fact that we're seeing the fluorescence already, I don't know. It's the color I'd expect. I just wasn't expecting to see it this early on. Another surprising development that's really got nothing to do with the chemistry is wasn't in the lab last week, and it seems like the bird took that opportunity to get back into the nest. It must have been, when was the last time that bird was in the nest? It was during the, what, neodymium video? I don't want to disturb him. Her? Him, her? We didn't even name him. I'm sorry. Are you there again? Did I hear you there? Alright, maybe I'm imagining things. Are we seeing any eggs? I can't see shit. Are any eggs in there? I don't know, there doesn't seem like there's any baby birds in there. So, maybe I'm imagining things. I swear the bird was here. Well, first of all, I don't really want her here. So I probably should have removed the nest if I don't want her here, because it's obviously such a well-built nest that she's coming back. I wonder if she'll lay some eggs. I probably should remove the nest before the eggs are getting laid. But I should really look at the video footage to see if there's any eggs in there before I go about doing that. Filter the DMSO, don't die, check if there's actually eggs in the bird nest, and if there are eggs, I don't know, guess we'll become a parent of even more baby birds again. Good luck, everyone. While we're trying to grow those perovskite crystals in the DMSO, I wanted to loop back to this lead flashing because I posted a picture of this on Twitter and YouTube or whatever, and people first of all roasted me for buying this much lead when I said I was going to use only a little bit. Like, why don't I just buy fishing weights? And that's a very good point. Probably should have bought the fishing weights. I just go to the hardware store more often than I go to the fishing and boat and tackle store, because just don't really fuck with the ocean. I know that's not very Australian of me, but just not really into the ocean. Anyway, the point is everyone also was saying how this is copperized lead flashing and the copper is going to present a big problem. And I was thinking about it, and it's weird that it just hasn't come up, right? We dissolve some in nitric acid, and we'd expect, even if it's a small amount of copper in the lead flashing, it to turn blue, right? Because copper nitrate is very blue, so even a small amount of copper would dissolve in nitric acid and turn the nitric acid blue. But everything has been extremely not blue. So I wonder if my physical melting and kind of pouring off the lead from like the slag or whatever from the lead actually separated out the copper, or there's just not copper in here, or maybe the copper levels are so low that it's not even turning the nitric acid solution blue, in which case the levels are really quite low. I'm just going to cut another 10 grams or so and not do anything to it and just directly put it in the nitric acid, and we'll see if the nitric acid turns blue. I think I just find it hard to believe that something I attempted actually worked to do the thing that I wanted it to, which is melting the lead to separate it from the copper. If that actually has worked, that's fantastic, but I don't know, weird. Anyway. Also, I happened to buy some of these lead test swabs. So, I mean, important, is this lead? Will it pass the is it lead challenge? That's lead. Yeah, that's lead. That's what the test looks like when it's positive. Not a stark colour change that I expected, but it's still there. That's lead. Alright, I dissolved that 10 grams of lead up in a very minimal amount of solution, and really there's no colour to this at all. There's no blue colour, so the amount of copper in this must be extremely low. Well, I mean, not like trace levels, but certainly less than 1%. It's really hard online to see how much copper is actually in copperized lead, but really I think for most purposes you could use this lead. So this lead will be fine for this purpose, and for generally most purposes. The one exception I will say is with explosives. A small amount of copper and lead is very bad if you want to make something like lead azide. Copper azide is much more sensitive. It's extremely sensitive. So it's much more sensitive than lead azide. So if you use lead nitrate with a small amount of copper nitrate in it for that synthesis, you're going to make lead azide that's contaminated with copper azide, which is just a tremendously bad idea. I will label this as such, that this is a potential copper contamination, and I shouldn't use it for any explosives work, but yeah, I don't know. If the lead itself hadn't said there was copper in it, or didn't say it was copperized, once again, it hasn't actually said it's got copper in it, it just says copperized, doesn't mention copper anywhere else. But if you had said that, I wouldn't have I wouldn't have known. I would not be able to tell you that there's any copper in this. For once, something is actually cleaner than we thought it was going to be. Anyway, we've now got, 10 grams of lead dissolved up. Crystallize out all this lead nitrate and store it for next time we want to do lead chemistry. That's not explosives lead chemistry. We can use this. I was not able to get any orange crystals at all of the perovskite growing. So I tried adding ethanol in there to try and precipitate out some perovskite, and it kind of worked, but not in the way I wanted it to. It was certainly starting to precipitate out, but once it all mixed, it all resolved, and then it kind of got cloudy, but not cloudy with orange stuff. It looks like a bit of white. I still think the ethanol anti-solvent bit is a good idea. It really does seem to work, so maybe I'll just go off book a little. This is just some water and some ethanol. If I take a drop of this and put a drop of it in the water, I assume that's the lead bromide precipitating out, whereas the cesium bromide, which is also dissolved, just dissolves into solution. So that's obviously not the thing we want. Whereas if we get another drop, and this time we put it into ethanol, look at that. That's the material we want. I think if I got a solution of ethanol, got it all hot, and then added this DMSO solution to it, it should precipitate out all of our material. I guess they're not as nice big centimeter sized crystals, but maybe if the ethanol is hot and then we cool it down, they might grow into crystals a little bit. I hope so anyway. Such a stark difference between the two, just depending on solvent, but hell yeah. All right, let's try that. We're just making that up, really. I'll put this sort of toxic lead thing down. We're obviously making it up as we go. It seems to work, and at least is a way to recover all of our material, because we have, nearly 15 grams of perovskite mix dissolved up in here. So even if we get a couple crystals, it's not really a lot. So this seems to actually give us most of our solid back.